Okay. So, firstly, I guess on the project front, quite important that when you talk to me. I mean, I think thus far I have had two groups speak to me, and there's a group which is of my own students. So I guess three groups. So vast majority of the class hasn't. And the projects that I described last Friday, you are not limited to them by any means. I mean, they were just ideas I'm throwing at you guys, but start the conversation. Today in the office hours, I was 15 minutes late, so I don't know if any of you came and missed me, but unfortunately, some visitor from ARM, the meeting ran over. So what I'm going to do is I'm going to stay after the lecture for a bit also, so in case you want to come and talk to me. Also tomorrow is afternoon is a good time. I can again kind of talk there, but drop me an email. The other thing I would mention is that just generally if you don't find me in my lab, in my office, then come to my lab. Kind of usually one of the two places. Okay. So any questions firstly about any of the project ideas that I threw at you? Okay. By the way, also I want to suggest that the ideas that kind of come out of my students often tend to be, at first blush at least, on the harder side because they're kind of producing them out of their research ideas. So, but once you start discussing, we kind of derate them to a level where it becomes more meaningful. Okay, so just something to bear in mind. But let your interest kind of drive things. So again, questions, anyone? So today's lecture, so last time we looked at the ways software gets organized, and we looked at different ways a processor can get shared between software modules, different notions of software modules. We talked about events versus threads, and whether it's events or threads. In one case, we have sort of concurrency of sorts, and in case of events, is function calls. Deep down, there are a couple of things which are happening. Number one, you have the operating system or some runtime system has to somehow decide which software module gets to use the CPU at any given point in time. And some of it is decided at the hardware level, so interrupt handlers always get to run unless they have been disabled. But a lot of the rest is really decided by the operating system, by the runtime system. So for example, when I talked about the embed OS and I showed you kind of those different states the threads could be, waiting and ready to run and stuff like that, then moving a thread moves from one state to another almost automatically, except for one very crucial one. When do I make a thread actually run on the CPU, and when do I bump it off? And that decision is at the heart of what is referred to as CPU scheduling. And you can take these concepts and kind of apply them to a lot of other resources also, like a sensor or a radio or things like that. But moreover, that decision will be not very interesting unless there was something that was constraining it, and something that you were seeking to optimize. And so usually these are things such as timing, power, maybe even things like resilience or cost of running. And for example, if you're running things on a cloud server or from some place where you actually have to pay money, those kind of considerations will come in. Of these, timing and power tend to dominate the discussion. Sometimes they are a constraint, sometimes you seek to optimize them. So in some systems you might say, I have a hard constraint, I must meet it. In other cases, I may have just a desire to optimize it, like I want it to be low latency, but it's the same set of metrics. So what this lecture I'm going to do is spend some time discussing the type of timing constraints you encounter, and then also how they translate into the algorithms that the operating systems use. And I'm going to cover kind of very basic versions of these. There are a whole bunch of other types which are encountered in more complicated systems. Now, at the root of all of this is the need to design these embedded systems or the code you're writing in a systematic manner. So it's one thing if you are designing stuff which is in systems which where failure is not catastrophic, right? I mean, if my toast takes a few milliseconds longer to pop out of the toaster, who cares? On the other hand, there are settings where the same failure can have very dramatic notions. So much of embedded systems software was historically been driven by essentially people who enjoy hacking, and therefore the approach to designing these systems have often been very ad hoc in nature. You put something together, you run it, see if it works, and if it doesn't, you go patch it, and you go through that cycle. The problem with that is that failure, I mean, I'm sure you've all heard of terms like Murphy's Law and all. The problem, any sort of this ad hoc testing doesn't capture all the failure modes. So you might think it's working, but actually it will fail once deployed in the field. So very important that when you're designing these things, you do in a manner where you can a priori make a statement about the system, that if it will fail, under what condition would it fail, will it meet its requirements, those kind of things. So that requires a more systematic approach, and in particular it requires that you understand the ramification of, if you have an algorithm which is deciding when to run a thread or when to bump it off, will it under some condition fail to meet the deadline, those kind of questions. A big constraint or big confounder on these systems also is unpredictability or uncertainty. Your predictions from a model are only as good as the model that you have, and a lot of things about embedded systems we can't fully a priori anticipate, or if we can anticipate, it would be a very conservative system design. So just to give you an example, a lot of the theory and all, we kind of go with the notion that, okay, CPU has some frequency and therefore some speed. With it can process things. And even in systems that we can change the frequency, it will happen under software control, so therefore we will know what is happening. But the reality is a lot more complicated. Modern processors, since they have begun to burn so much power, they also have thermal governors built into them. And if the heat starts going too much, then the hardware kicks in and it will slow down the processor to avoid damage, irrespective of what the OS is doing. So that's an example where under certain deployment conditions, your system may not meet the code. So environmental conditions come into play, right? I mean, the outside temperature, those kind of things. Another factor which comes in is that a lot of these systems are so-called multi-tenant systems. There are multiple things happening on them, and you may not anticipate how much work other things might need, and therefore the load may be more than what you anticipate, and that can cause problems. So uncertainty of various forms comes in the way of this predictable design. And the history of these kind of systems is littered with plenty of examples of failures that have happened because something failed, and I've kind of cited a couple of examples, which actually both of them have to do with timing related issues. And since then, I mean, in recent years also there have been other incidents like these. The first one is the very first Gulf War, and there was an incident there where an incoming missile from Iraq ultimately ended up killing a bunch of American servicemen because the anti-missile system that they had failed to shoot it down, and it failed to shoot it down because it had a timing error. And the nature of timing error was that somewhere in the software loop there was a very tiny amount of accumulation error in how much time has elapsed, and therefore that the longer the system ran, that error accumulated more and more. And since in an anti-missile missile system, it has to predict the speed of the incoming missile and the location, so that prediction became wrong. So the missile, whatever, the anti-missile missile, the Patriot missile was shot, but obviously ended up going to the wrong place. So that's an example where lack of good time ended up translating into bad location, and in turn ended up causing the system to fail, and then some other damage happening. Another often cited example is, excuse me, one of the first robotic mission to Mars. So this was this little rover, and after it landed, it started rebooting a lot. And eventually, I mean, like what you hear in the excuse me, that it's a software glitch and stuff like that, but deep down it was actually a very predictable timing error that was happening, again because of shared resources. So in effect, last time I had talked about those mutexes and semaphores and stuff like that. So deep down what's happening was that there was some place where one task was grabbing a resource which the other task was waiting on, and it turned out that they had underestimated how much time one of those tasks is going to run. In particular, there was more interesting data being collected by some scientific instrument, so it presented a higher load. It resulted in that task grabbing that shared resource for a longer time, which caused the other task to miss its deadline, and in turn kind of caused the reset using that watchdog timer which I talked about last time, and that would cause the robot to reboot again and again, and eventually they patched it. Plenty of other examples, the Air France crash, the Toyota car issues from a few years ago were also attributed to some software issues, and a lot of time these systems are so complex that we just have a hunch, we don't even know what is going on. One field which is currently kind of gained a lot of prominence is that can you analyze the software or hardware to make assertions about its safety and all, okay, and it's a pretty complicated area. Industries in which you put in where the cost of iteration is very high, they have sort of developed much more systematic procedures. So when Intel puts out a chip with a $1 billion upfront cost or whatever, for they take a lot of care. On the other hand, in software, since it's very easy to iterate, so things tend to be a little bit more ad hoc in nature. So yeah, these examples. Okay, this is another one, the very first flight of space shuttle, and in this particular case, software was tested. So this is one thing, testing or simulating or sort of testing is never sufficient because you can never do exhaustive testing. So really kind of to show that a system is not going to fail, you have to sort of prove it. But the problem is anytime you attempt to prove it, it is going to be under some simplifying conditions about how the world is behaving, and therefore again you miss out things. So in reality you have to do a combination of things. You are simulate, you are going to test, you are going to formally verify, and yet bad things happen. In this particular case, there was a bug which they later found had a 1 in 67 chance of occurring, and that is what happened on that flight. Okay, so you sort of this Patriot missile case I kind of already talked about, but basically in this case there was some software loop which was causing an accumulation of 57 microseconds per minute, very tiny amount of delay. Then you model the software, right? I mean, and we'll see how you can begin to systematically take into account these things. So a lot of these things can be analyzed. The challenge was that a lot of theory for doing this, or the models for doing it, happened after these things had already happened. I mean, I'm talking about things which happened in mid-90s through since then, okay, and continuing to this date, okay. So these things were happening in an era where our understanding of these kind of behaviors was pretty rudimentary. The scheduling algorithms didn't exist, and also it was truly black magic kind of things in those eras. Now things are better, but still not so much to this date. I mean, designing these systems in a manner that you can make a guarantee they will not fail is pretty challenging, because you cannot make any guarantee about the physical world anyway, right? I mean, but still a lot of stuff, sort of a lot of things have happened. Some other sort of very famous examples, okay, so in the past, in 90s, there was a whole episode where Intel processors had a floating point bug. That is, some numbers it would add and it would fail. Java virtual machine has a problem with for a long while with certain esoteric floating point numbers. Last year there was this whole hoopla about, and continues to this date, that a lot of optimizations that have been done in modern processors create security vulnerabilities and they could be exploited. And the thing is, each one of these things, in hindsight, one can say, yep, I mean, it exists. The challenge is that, and continues to be that, can we make a process where we can catch these things in advance? And the answer is really no. I mean, we are going to learn from mistakes, but the mistakes are going to be costly. Crashed, whatever, space shuttle or whatever, those kind of things. So this was a Patriot middle thing. 57 microsecond per minute sounds nothing, except that time the system had been operational for a long time, so it had translated into a delay of 343 millisecond. And even that doesn't sound much, except that 343 millisecond at the speed of an incoming missile is a substantively long distance, and therefore the Patriot missile missed its target. Lots of examples of bugs which ultimately relate to the underlying issues of timing. And timing, as you can see, translates to distance. Timing translates into coordination things. Timing translates into sequence of things. So anything to do with timing becomes important. Power is in the same way, because modern systems are designed to be operating very close to the margin. Okay, so anytime a thermal overload happens and all, the system will slow down and the kind of bad things happen. Just to cite things, thermal is related to timing performance and vice versa. So these failures often sort of carry over also. So long story short, timing constraints matter, power related constraints matter, and other such thing, and their failure is failure to meet them in turn translates into other bad things happening in the system. So with that bit of motivation, one of the things that sort of pops out of it is the importance of doing things in the system in a manner that will meet timing constraints that exist. These timing constraints can come in a variety of forms, so we are going to look at them very shortly. One of the key problems that arises is that my processor is being shared among multiple tasks. Can I do that sharing so that timing constraints that I have on the various tasks are met, and do so under a variety of situations? Like, for example, I may have dynamically arriving tasks. I may have many processor cores. I may have tasks with complicated temporal behavior. Sometimes tasks are very periodic, at other times they are highly unpredictable. I may have tasks which have state versus not. So by state I mean one invocation of the task does something, and then I have some information that I need to carry over to the future one, so I have to kind of worry about that. I may have tasks which are dependent, like one task needs the data produced by the other task. Tasks may have different, maybe non-preemptive, like for example, they really don't want to be disturbed. So remember last time I talked about these rare but long-lasting tasks can be a pain, because and particularly if they are non-preemptive, then you have to be super careful that you do them at a time when you really something important is not going to happen. So a variety of issues sort of come up. So let's look at timing constraints a little bit, just to give you a flavor of what we encounter and what kind of issues are there. So firstly, at a very high level, there are two types of timing constraints that arise. There are timing constraints that are constraints related to the performance. So they limit the response time of the system. And then there are constraints which are on the behavior, and they basically place demand on the system. So what I'm referring to is there are constraints arising from because the system is unable to do certain things. Okay, it just takes time to do it. And then there are constraints arising because the external world expects us to react that way, and if we fail to, then the overall system fails. And then furthermore, these constraints themselves arrive in kind of three broad categories. Those which are maximum related, like some timing constraint, it will say this time should not be more than some threshold, or minimum related, that this time interval must be greater than some threshold, and then finally durational, that is something must happen for some duration of time. So usually these kind of things, I mean, there's a whole sort of theoretical side of computer science which deals with events and how do you reason about these things and all. But let's just look at some examples that might occur of these different categories. So let's look at maximum timing constraints. And I'm going to use the term S to refer to stimulus and R to refer to response. So S is an event going into my computer and therefore from the outside world, and R is an event produced by the system and therefore going to the outside world. So you can think of S as a sensor data coming in, and R is the actuation command kind of going out. Okay. So first category is an SS type of thing. So basically, like I'm using a telephone system as an example, second digit must be dialed no later than 20 seconds after the first digit. Okay, so it's basically saying that if the user is punching these numbers in, then the user must punch the next digit within 20 seconds of the first digit. And presumably kind of the idea out here is that we are trying to distinguish between user who has just walked away. At some stage the system has to time out and not wait for this. So this is placing a constraint on the user because this is an event coming into my system, and therefore it is saying something about, at this point it's saying something about the user, that the user must obey this maximum constraint. Another one is an SR type. It's the stimulus to response. A max time is allowed between the arrival of a stimulus and the corresponding response that is happening. So like for example, after I lift the phone, I expect the phone to present me with a dial tone pretty quickly. So that could be translated into a constraint of this type, that the input event to the system is lifting the phone, and the response event from the system is the dial tone. And we are basically saying that should not happen more than 2 seconds later, and this is now a constraint on the system. That is, presumably the computation inside the system has to be fast enough. So again, the first one is a constraint on the user has to be quick enough. The second one is a constraint on the system has to be quick enough. RS is response to corresponding stimulus. So the system does something, like moves something in the world, and the world reacts, and then something sort of comes back. So max time like this. So for example, after receiving the dial tone, the person shall dial the first digit within 30 seconds. So I lift the phone, the dial tone comes, then I have 30 seconds to go back. So again, you can imagine these kind of things happening in a lot of systems that you interact with. So this is a constraint on the user. And then finally, response. So in this case, the system is producing 2 responses, and there's a max time allowed between those. So after the connection is made, the caller will receive a ringback tone no more than some time later. So in this case, we are basically saying 2 actions performed by the system must happen within a certain interval, and therefore this is a constraint on the system. And essentially I've covered kind of all the 4 cases. 2 translate into constraint on the user, 2 translate or the world, and 2 translate into constraints on the system.
So like constraints on the system, is it like constraints on your device plus the constraints on the network, or is it just
whatever is behind it?
So
like for example, in some of these things, your telephone, like for example, the ringback tone is really a constraint on the whole telephone system, right? Not just the telephone, because all of this means that your phone is going to talk to the switch in your local exchange. That local exchange will talk to wherever, all across the nation or the world, and then right, I mean all of that. So it's the whole telephone network behind this.
if someone calls me on my phone, I press the accept button, and then do you like network bottlenecks, or do you like my dialer hangs or something? So where is this implemented? Like who?
Depends. I mean, old style telephone systems, your telephone did very little. Everything was between the telephone exchange or the telephone switches all across the network, and they were designed very carefully to provide these kind of things. Nowadays, things are a lot, like for example, if you're using voice over IP type, like internet-based calling and all, they do things very differently than your good old phone. So where things happen is kind of very different. But for all purposes, you can say that from one phone or whatever, one PC in which you're running Skype or something, all the network, and then the other one, that whole thing is a system. So when we say that something has to be done by the system within a certain time, then comes the second issue. Whose responsibility is that? Is it that I have a fast phone and a slow network, or a fast network and a slow phone, or where do all of these things reside? And that's a separate issue which one has to engineer do. But what this is saying is, whatever my system which is responsible for producing two responses or a response corresponding to a stimulus must meet that, and then you have to take this delay budget and kind of budget it down. Now, take another example. A lot of times we play games, multiplayer games, which run on servers. So I do some action, you are also playing it, and then eventually all of that has to be seen by you, and you do some action and I kind of see it. And for the interactive game to work well, that latency has to be low enough. But what all is involved in this? Well, my computer, the network to the server for the gaming company, the delay in the server, the network delay back to the other user, and then finally delay in that. Okay, and all of this has to be divvied up somehow, right? And kind of companies who design these things and all, I mean, obviously sort of take into account but still there would be unhappy users. I'm sure you have heard about that, how gamers go out of the way to speed up their machines and all, going to like ridiculously low latencies and all, but that's still playing at the edge. If they are now sitting on, if they are in these kind of games, then of course the server delay and all kind of matters a lot. So the whole system, or in case of telephone systems which also have video, humans are pretty sensitive to discrepancy between video and audio, in the sense that if I see someone's lips moving and if they're even a tiny bit off, then the corresponding sound we notice. In fact, that threshold is as little as 10 milliseconds. So in that case, there are two responses the system is producing, the audio stream and the video stream, and they need to be tightly synced. So there are a variety of these constraints. Okay. How to meet them, we are going to just look at a very simple example, very simple variant of that in the course of this lecture. Minimum timing constraints, they are kind of the counterpart. So again, there are examples I have given. So a minimum between SS so minimum is basically saying at least this much time, right? So a minimum of 0.5 second must elapse between dialing of one digit and dialing of the next. Okay, so this is a constraint being put on the user, that don't dial too fast, but perhaps motivated by technology limitations, right? I mean, we basically know that it would be very expensive perhaps to design a system which can handle digits being pressed very rapidly, and therefore we are telling the user be slow. Or SR, after the caller has dialed 0, the system shall wait 15 seconds before dialing. So basically there's a gap being implied. In this case, it's a constraint on the user. So the purpose out here is so that the user can do something else, and kind of a couple of other examples like these which you can go on your own. But they are all like either translate into a constraint on a user motivated by a limitation of the system technology, or a constraint on the system motivated by perceptual limitations that humans or the world might have. Okay, so one side is a motivator and the other side, and a big part of kind of early stages of system design is simply coming up with these constraints, right? I mean, what is technologically feasible, what makes sense, what can we cost effectively achieve. You can't just go and set goals in the vacuum. Like for example, if certain data rate is expected, over the lifetime of this project, do we expect technology to be there so that we can achieve those data rates, right? So it's a dialogue between the technologist and kind of the application side of the people who are thinking about the user experience. There are other timing constraints which are a lot more complicated, which may not simply be min-max between two events the way I have done. Sometimes they span multiple events. Like for example, I may have constraints like the user should dial 7 digits in 30 seconds. So now in this case, we are really placing a constraint on a bunch of events, okay, as opposed to kind of just a pair of events. They may also be expressed in terms of durations and all. I'm sure you have dealt with these systems like press the button for 5 seconds, but no more than 8 seconds, and then release them in the sequence and all. I mean, we encounter them on our phone for the hard reboot and all. So those are examples of kind of complicated looking constraints, right? So I have some examples of that here as well. So kind of the theory behind these and all. I mean, again, one place where people encountered them very early on was at the component level. So if any of you have ever done hardware design, when you interface a CPU to a memory or a peripheral to a CPU, there are all these timing diagrams that the chip come up with, right, for the signals that go back and forth. So a lot of work in 90s and 2000s kind of went after that. Distributed systems have often dealt with these things. Actions happening at faraway computers across the network, including the telephone system, or things happening in a data center, they all need to be carefully orchestrated. Nowadays, one system which is very, very timing constrained is the whole financial system. Possibly some of you may have read kind of articles about these, that how companies try to locate their servers right near the New York Stock Exchange so that the response time could be very rapid. But that's only part of the story. In that case, they're just worried about the latency because the information is in the exchange and they want to be able to respond to it, and kind of microseconds matter in terms of giving an edge to your trade over the others. But the other issue which comes up there is being able to, the forensics. That is, if something goes wrong, let's say there is a huge crash in the stock market, then SEC or the other similar agencies in the country, they want to go in and analyze that someone do something bad. So at that stage, timing everything, what was the sequence of things that happened, all of that is very crucial. So some years ago, European Union mandated that all events in the trading system should be time-stamped to nanosecond accuracy all over the planet. Not achievable, a lot of hue and cry, so they kind of slacked off, and now it's kind of more at a microsecond level, single digit microsecond, but pretty challenging if you think about, you are kind of looking at examining events in a distributed system at that granularity. But in many cases, these are important and they do matter. I mean, experimental physicists and all face some of the most tightest timing constraints because they are dealing with sort of phenomenon happening which are very rapid. Companies like Google and all, with multiple data centers and all, where they're coordinating distributed databases, they face these kind of problems also. And at a more mundane level, even the embedded system running in your microwave oven has timing constraints. They exist everywhere, except the severity of them is considerably different. So as a result, the ability to support time and perhaps even requirements on time has received a lot of attention. So there are two types of support that you might expect. One is support that lets you do time-driven things. That is, I should be able to say, do this and then wait for a certain time and then do something else, or like do something at 5 p.m., those kind of requirements. And the other one is that I create a system, but then I also want to say that, and I want this action and this action to be no more than 1 second apart, for example. And then I want some tool to tell me whether that would be the case. Can I run it on this processor and expect that performance to be met, right? So an assurance is one part, that's the second one, and an expression of something that I want to do. So as a result, support for time has emerged in languages, at quite languages and design tools, and sometimes it's directly native to the language, and sometimes it is APIs that are offered to you by the underlying operating system. Insofar as you as an application developer is concerned, kind of doesn't really matter at some level, but having it as part of the language gives that advantage that the compiler can analyze it. Having it as part of the operating system has the advantage that the OS can do things which a compiler cannot, because compiler doesn't have control over the runtime, what's happening in the runtime. So at the very basic level, you would see support for measuring elapsed time. That is, I did some action and I'm going to later do some other action and I want to elapse. Like maybe let's say I made a function call and I want to measure how much time that function call took. So how would you measure? Let's say you were writing a piece of code on your whatever Unix computer or Windows computer, and there's a function call that you made in your function. How do you measure the time taken by it?
I record the time before I execute it. I record the time after it gives me the output.
Yeah, so I want a bit more specific. For some system that you know, how do you get the time that?
Did you count the clock cycles?
That would be pretty hard.
Usually there's like some kind of timestamp that's provided to you, like either the API or the operating
Yeah, so
system.
do any of you know some API for some operating system or some language?
So like in Python, you can just import time and then get the transparency.
Right, great, yeah. So in Python, you can just import time. In Python, actually, there's also a very cool package where you can say, you can give it as an argument the function you want to call, and it will run it bunch of times and tell you how much time it took. Okay, so Python has sort of good support for time. But every language or every combination of language and operating system do. So like if you're running C, doesn't have anything natively built in, but then if you're running it on Unix, there are functions like get time of day, and even sort of finer granularity timers. So kind of the concept is you call it once, you call it next time, and you subtract the two. But then there are many types of times within that, right? Anyone ever use any of those functions? Do you recall what does it just, like Python just returns one time, but let's say, so.
You can call NTP server,
Huh?
you can call the NTP server and get the time there.
No. When
No,
you, how,
system time versus
there is system time versus user time versus, right? So what's the difference?
So like system time, for instance, you would have the OS and it has its own like computer clock, and then you'd have the, for example, with Windows, it's like millisecond order. Where you
I think BIOS time is different from OS time sometimes.
That's kind of a non-issue for the most part, because BIOS time matters at the BIOS level, but once the OS starts running, it's on its own.
Usually the OS, right? You just get
Okay, no, so usually you will see in Unix-like operating systems, and which is also Windows. Windows deep down runs the good old Mach kernel from CMU, modern Windows. You see three times. One is the wall clock time. Okay. The second is the time that for which you actually use the CPU. But remember, we talked about last time that your thread may get bumped off and all. So I called the function at 4 p.m. My function returned at 5 p.m. The wall clock time is 1 hour, but during that time it may only have 30 seconds of the CPU. So then the system time is 30 seconds and not 1 hour. Okay, so system time is telling how much of the system was used. And then finally there's something called the user time, because remember, within this time, due to those system calls I had mentioned, a lot of time you are making a system call and then the OS is doing the work. So they also make a distinction between the time your code did versus the operating system code did. Okay, so you kind of make a distinction between the two also. So your code plus the OS code will add up to the system time. Okay, and if the purpose is optimization of some form and all, you would do it. Depending upon what you're trying to do, one or the other time might matter more, right? I mean, for example, if I'm trying to optimize my code, then system time or user time, those kind of things will matter more. On the other hand, if I'm trying to measure a physical phenomenon, then the elapsed time according to wall clock will matter more, right? If I'm trying to coordinate with something else, then it's the wall clock time which is matter. So measuring elapsed time, and modern systems now have timers which go down to nanoseconds. Okay, so you can timestamp at that level. If you're running on Intel processors, there is a instruction called RDSC or something like that, but it's an instruction which lets you read the hardware timer. Okay, and you can kind of and you can call it as a standard application, so you don't need any special permission for doing it. But there are so that's the, you were talking about counting the clock cycles, so that comes the closest that you have. You can read that timer. There are some caveats there, like for example, remember your processors are put to sleep. What happens during those time? Am I still cycle counting or should I not? So there are subtleties and things have changed over time, how things are handled, but there is an instruction like that. Okay, so measuring time, delaying a process. So I basically, in effect, I want to sleep for a while, right? I've done something, then I say sleep for some time, and now I want to do it later, right? So I defer it for a later. So a variety of ways. There are function calls which basically say sleep for some time. In Unix, you have something called sleep 5 seconds. And then what happens is when I say sleep 5 seconds, under the hood, I'm put into the process is put into waiting. It's really waiting for an event from a timer. Operating system sets up a timer, and when the timer event happens, then you're moved to ready to run, and then eventually you get the CPU. A lot of things may happen. You may say sleep for 5 seconds, but in reality, after the timer happens, maybe something higher priority is running, and you may not get the CPU immediately, so it may be a little bit delayed. And then there are transition costs associated. So all of those things have to be worried about, but conceptually, is delaying a task. Timeouts. So sometimes you do things where what you want to do is you're basically saying, okay, read the next entry from the queue, but the queue may be empty, and but you are willing to wait for a while. So you basically want to tell the system, I want to read something from the queue, and I'm willing to wait, but no more than 1 second. Okay, so that's the concept of timeout. So in effect, I'm doing something, or I've asked the system to do something, and in parallel, I've told the system, start a timer, and if I'm still not done and the timer fires, then bring me out. Okay, so that's timeout. And again, many of the API calls will have things like these. Even your trivial stuff like read and all will have that, read from a file, but with a timeout attached to it. And then finally, a deadline. I want this task done, but I want it to finish by 5 p.m. Just as simple as that. This gets into kind of a more hairy kind of thing, because the system has to worry about when should it do it. So if the deadline is far enough, it's giving the system the freedom that, I don't really need to run right now. You can, if someone else needs the CPU more urgently, you can go ahead. But then you also have to anticipate that not to make it too tight, perhaps, because maybe some other even higher importance tasks may come in, and then I may not get the chance to run. So somehow the system has to balance what other tasks are doing and what your requirements are in terms of timing. And these are just some examples. And again, like I said, there is a combination of compile time and runtime methods which achieve those. Question?
I was wondering, so is there a case where it executes like after the deadline?
Usually when there is a good question and no easy answer to it. Okay, so one view is that for certain kind of things, deadline miss is catastrophic, and therefore if you're going to miss the deadline, you will not continue, but you will probably call some sort of grace handler. Okay, so that's an exception condition, and you're going to do something about it. So if I miss the deadline, if its consequences are going to be that the drone is going to crash, then you are probably going to invoke a safety routine of some form. Yeah, so that's one. Another possibility is, and I think I removed that from the slide set. But sometimes what it happens is when the system realizes and says, I'm going to miss the deadline. So it's going to tell your code. It's going to send an interrupt to you saying, I have event to you saying, sorry, but the deadline is going to be missed. And then you can take some corrective action. Like for example, instead of your original algorithm, maybe you can run some faster, quicker, but less accurate algorithm to kind of do it. So how you react to deadline misses varies, and in some cases you do nothing, the system crashes. Okay, and other cases, yeah, you keep running, and in that case, all it means is that deadline was soft. So in many applications, occasional deadline misses don't really matter because the world is adaptive. So for example, if you're watching, let's say, YouTube video, right? I mean, I don't know about you, but I've often encountered like this buffering message, okay, and this kind of just spinning wheel and all, okay. It's not that I'm damaged or anything like that, it's just annoying, right? So in those cases, it's really more of a unhappy user as opposed to whatever, a crashed aircraft kind of difference, right? So it depends in these scenarios. So a lot of examples are soft in terms of their requirements, but there are also some hard deadline systems as well.
So, like, would a deadline be a hard or soft deadline on basis of if the system is safety critical or not?
Well, or another way of saying is safety critical systems are usually the ones where there are hard deadlines. Yeah, but you're right. That so let me also say, it's not simply safety critical systems. Sometimes hard deadlines exist in non-safety critical systems, but if those deadlines were missed, really bad things will happen, like your USB will not work and data corruption will happen, and that will leave a really, really unhappy user. So fundamentally it's about what damage or level of annoyance results from a missed deadline, and that's very application specific. There is no general statement you can make other than that in any system there are going to be some deadlines which are going to be much more important than others, and you take them into account. Okay, so the variety of these time related features, and you might want to just reflect from your own programming experience, like what kind of time. Also our interaction with time sometimes is really about relative times and all, like, right? I mean, sleep for 5 seconds and all, and sometimes it's about absolute time, like sleep until 5 p.m. Okay, so now you are really referring to some global time, and you are and that introduces its own complexity, because it's one thing to have a local timer and cycle count between two events, and it's entirely another thing to synchronize or maintain somehow learn information about how to map the reading from my timer or my local timer, my local clock, to the worldwide accepted reading for the time, which is called as UTC, Universal Coordinated Time, which is actually is a very interesting tidbit which I, despite having worked on time area, didn't know until a short number of years ago. So we always see like 12 p.m. whatever 12:00 UTC, right? So UTC is the time maintained by some world authority and all. And I always thought that okay, it was sort of done by some set of clocks, and we kind of decide that. The interesting thing I learned was that you can't say right now what the UTC time is, and the reason you cannot say is because the UTC time is decided at the end of the day. So what I mean by that is there are a bunch of reference clocks on the planet, and they look at their performance over the past 24 hours, and then they average them, and then they decide what the UTC was for the previous 24 hours. Okay, so at any given time, the UTC that you are really getting is an estimate, and the real UTC is decided at the end of that 24-hour period, and then you kind of go back. Other confounders when you are dealing with the absolute time are things like leap seconds and all, which also confound things. So the moment you start dealing with our human construct of time, right, that it is 12 p.m. UTC or whatever, then you get into a whole bunch of other can of worms that are otherwise not there. So we're going to examine that part later in the course. for now, main takeaway is that there are these kind of capabilities that languages and operating systems expose to you, and sort of use them. There are real-time languages and real-time operating systems that provide more of these features, but even almost any system that you work with would have some notion of time, because we do need time even for interacting with the users. So now let's dive into a little bit into how we can translate these constraints and our goals and all into something. How do we manage? Fundamentally, which task gets to run on the CPU? That's basically the question. Okay, so now we kind of back away and we create kind of a formal, idealized, but simple model. Okay, and then that's all I'm going to present, but there are obviously more advanced pieces of work which kind of add far more details to it. So the focus here is going to be on a very just a small subset of those timing constraints, but it turns out that this is useful for a large fraction of a large number of systems. So the basic model is I have a bunch of tasks. You think of them as functions with state, and they're independent for now, so they don't exchange any data. So for whatever reason, obviously it's idealization. They never need to share any resource or produce data from one task and used by the other. These tasks are entirely periodic. So what that's saying is that think of it like this. Like I said, these tasks are like functions. So think of them as function handlers, event handlers. Sorry. So the corresponding events which invoke a task. So like task 1 is invoked every time there is an interrupt on pin number 1, for example. Okay, so that event arrives periodically. So it could be, I don't know, out samples from an A to D converter or some sensor or stuff like that. So in this particular case, T1 through Tn are the rates at which the corresponding tasks are being requested, or you can say at the rate at which they're arriving. So, okay. So the rate therefore is 1 over is the inverse, and then so now the same task, same function is being called multiple times. Every time the corresponding event comes, we fire this function, it finishes, and then kind of so multiple copies of them. We also assume that the initial offset. So remember, kind of the world started at some point. The system rebooted, t equal to 0. When did the first event corresponding to, let's say, task number I arrived? So one version of this would be, we can say, okay, I know that the first event arrived for task I at some delta I. So, or Ri, okay, so you call it the phase. In that case, if I knew that the first event of ith task came at R sub I, then essentially I know for all future when the other instances are going to arrive, because we already said they're periodic. So in that case, I really have a static system. I know upfront at compile time, so to say, I know when the events are going to arrive, and then conceptually I can just come up with a good algorithm to handle it and be done with it. I don't have to do anything at runtime other than obey that schedule. So I can kind of work out forever who gets the CPU at what time. It's a hard problem, but at least we could. But if I don't know that phase at all, if I don't know when the first event of the ith task will arrive, then today I reboot the system, it arrived after 1 second. Next month when I reboot the system, maybe it arrives after 10 seconds. Third time I reboot, maybe it arrives immediately, because remember, the external world is sending these events on its own will. When I reboot the system, may have nothing to do with it. So that phase difference is what we call as Ri, and here we are basically saying that we don't know that phase. So I cannot predict upfront when the events are going to arrive, but for a particular type. But of course, after I receive the first event of a given type, then I can from that point on. But I don't. But it's only at runtime that I'll get to do that. Runtimes C1 through Cn. So we are basically saying that these functions have runtimes C1 through Cn. Now this is a pretty complicated thing. Also, like if I give you a function and ask you what is its runtime, answer is it depends. In general, there are lots of sources of variation that may happen. Firstly, depending upon the data, the precise value of the data, value of the input argument, my code may take different pathways through it, right? I may have some if then else or for loops or whatnot, and so it might need to run the for loop different times, or may take the left path or the right path. So there may be many different control flow path, as they're called, between the entry and exit, and therefore the time taken can be considerably different. Another source of variation comes in is that many of the operations depend upon the precise value of the data. So like floating point arithmetic, there is considerable variation in the amount of time that those operations take. So for example, hardware may optimize for 0 values. So if you're multiplying by 0, it might just go through very rapidly. If you are multiplying by some other numbers, the actual multiplier kicks in. And actually things are a lot more worse. There are some special floating point numbers which are actually very tiny numbers. They are called subnormal numbers, and they're extremely hard to implement in hardware. So usually what happens is when a subnormal number is detected, then an exception happens, and then their multiplication division is done in software, because just doing that in hardware is, like I said, supremely expensive. So even simple things like add, multiply, let alone transcendental functions and all, can have high degree of variation in their timing. What other things you think can affect computation time of a function?
Platform?
No, on a given platform. On a given platform.
So like just kind of like doing that function itself, right? Like you don't pretend there's any other. Like,
Yeah, I'm running on a CPU. I run this function, and now let's assume it's with the same data value now, and I'm going to run the same function sometime later. So I talked about value could affect, but now we are ruling that out because I'm making the value the same. What are the other factors that can affect the time this function is going to take?
the compilation of like the program.
Again, that was already done, remember, right? I mean, my system is running.
If it's waiting on the user response.
No, I mean, it's just a pure function, so no external world, so just keep like simple, pure computation.
If there's throttling.
Huh?
If there's throttling.
Okay, throttling. Thermal throttling may happen just at the bad time, and that may affect things, right? So it's clearly a function of the frequency. So the time taken is that. Okay, so that's good. What else? So that's the fourth thing, right? Is there something else?
Voltage.
Just the same thing, right? Voltage, frequency. Yeah.
How many other processes are running?
True, but that will not affect the computation time. It will affect the wall clock time, but it will not affect the computation time. Caches. Anyone knows what caches are? Do you think caches affect the computation time?
Good, yeah. Depends on like if you can run the program in the entire cache, you have to like call.
Right. I mean, if the data that is needed by the program was already cached, then the function will run more rapidly than if it wasn't, then it will be spending some time fetching from the main memory, right? So cache state, was the cache warm or cold, effectively affects these things, right? So these are some of the sources that make even something as innocuous sounding as computation time for a function pretty horrendously hard to predict. Now, the notion of runtime here, we are going to say is the worst case execution time. So we have simplified things. We said, okay, all I'm interested in the worst case, because that's how we are developing the theory, because if I can meet the deadlines in the worst case, then maybe I have hope. But even this is hard. Even predicting the worst case time, I mean, you'll have to make all these things like cache is cold, slowest frequency, blah, 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 right? I mean, all those kind of things that you have to make sure you understand what is happening. Just to give you a sense of some, maybe 15 years ago or so, there was a paper out of Princeton where for a lot of signal processing algorithms, they had shown what's the ratio of the best case to the worst case time. Like if you do a JPEG compression of a 256 by 256 image, how much time would it take and all. And it turned out, I recall from the paper, almost most of the things of interest to us, FFT and JPEG and these kind of things and all, huge variations between the best case and the worst case, like 10x, 50x, 100x, that amount of difference. So again, this is one of those things where the analogy out here would be you're designing, some of your circuit designers, you're designing a circuit, what's the fastest clock speed? Fastest clock speed is decided by the critical path through the circuit, and you have to identify it. So likewise, through the software, there is a critical path, and you need to know that and take into account all these other factors I was saying. What was the value of the numbers? Would I be receiving these special floating point numbers? All of those things have to be accounted for. Okay, so that's runtime. Relative deadlines. So relative deadline refers to that when the event for a task arrived, and therefore I invoked the function corresponding to that task, to the time when it must finish. So usually I would have constraints like when the event arrived, make sure that this task, the function that I call, finishes within 1 second, right? So that's the relative deadline, from the arrival of the event to when we expect it to finish. Now, very commonly in our systems, we encounter the constraint of the following type. If an event arrives for task number I, then I want this thing to finish being handled before the next event of the same task arrives. So it's like a sensor is sending me samples of data, let's say frames of a video. So we want to just keep up with it. So that timing constraint basically says that the relative deadline for handling a frame is equal to the interval between two frames, because I have to finish handling a frame before the next one comes. It's a very commonly thing, because if I consistently fail to do it, that means my system is overloaded, right? So a lot of systems, particularly things which are handling continuously sample streams of things, I mean audio, video, sensor data and all, they often fall into this category that relative deadline is equal to the time period. D sub I is equal to T sub I. But in reality, these are independent, right? I mean, it could be that D sub I, the relative deadline, is much smaller than the period because I have a delay budget. Remember I talked about that humans are very sensitive to delays in acoustics and all, right? I mean, so even though acoustic sampling may be done slower, but I don't want my phone to waste a lot of time. I want it to do its job quickly so that I can perhaps give more room for the network to use that delay. So in many cases, D sub I can be less than T sub I. D sub I can also be more than Ti because I may have a pipeline system. So an event arrives, the system begins to handle it. The next event of the same time arrives, but maybe it can be handled on another processor. Okay, so but again, for simple systems and for now, we are just going to assume the special case. D sub I is equal to T sub I, and that's a very common model you will encounter. That you're basically saying, let's keep up with the rate at which the samples are arriving. Other assumptions: all tasks are fully preemptible. That is, I can stop a task at any point, save its state with zero cost, and restart it. Again, not true, because I cannot preempt in the middle of an instruction. So if an instruction takes, let's say for sake of argument, a microsecond, that means that I at least have a 1 microsecond problem. That is, the instruction may have just started, the event comes in, I have to finish the instruction. I cannot stop the processor in the middle of the instruction. In processors like the Intel processors, where instruction can take many clock cycles, that can be a significant problem, because under certain circumstances, certain instructions on Intel processors and all can take hundreds of microseconds, okay? Because they themselves are pretty complicated internal things. So that can be an issue. We are also going to assume that all the operating system overhead, like movement of those threads from different states and all takes no time. Okay, again, not really true, but but a common assumption we can make, and then kind of a lot of work kind of then patches the basic theory to kind of account for those. So let's take a 5-minute break, and then we go into how do we actually begin to schedule things under this model.
It's not very much like so in your small methods you're about like having something that can potentially like just moving or something, or we just have to use it for the motion one could be like slow on maybe it does. That would increase the bulk. Very much.
Yeah, probably.
The four cases where you're not moving now, like just sitting there. No,
I know.
because like you're just sitting down, you're not really
You're probably just heart rate less.
we were just going to see if you pitched the idea to you, but
But maybe right after the lecture.
That
doesn't.
There's something I have to go to at 5:30.
Okay. Okay. Why don't you pitch?
Oh, straight out.
Yeah. Okay, so where we started, it's like
Elevator pitch.
elevator pitch, right? Okay. So sorry, we just got the idea. It's right, it's an elevator pitch, but okay, we'll try. So the idea is basically based on someone's mood, how you're feeling. So it's based kind of off the conceptualized idea. Based on that, we're still looking to how to best measure or estimate how someone's feeling. Based on that, we have a user recommendations and stuff.
Okay. Yeah. There are papers which show you how to measure stress, and in fact there are even apps and all which claim to, but usually they all basically, so stress is measured by heart rate variability. Okay. Variability in heart rate. It's called HRV. Okay. And respiration. That's the other one. And the third thing is sweat or whatever, right? I mean, you've seen those things where lie detector test kind of thing, right?
Skin conductivity.
Yeah, yeah, skin conductivity, okay. So heart rate, HRV, you can, I can give you some hardware which measures HRV. This experimental hardware from Ohio State University, but I will put you in touch with a student, and I can point you to papers from collaborators of mine who have, at least I think there is MATLAB models of stress. That's probably the best medically validated stress for variables that I know. Okay. And then you can build everything else. Okay.
So we just want to know, like, is that too simple? Because we were thinking more like like if you were studying crafts, then we would like recommend music based on how you.
Yeah, I think you'll still have sufficient challenge in terms of making the whole system there. And you can do it as a combination of stress and physical activity. That's the other thing you can bring into this. So physical activity one was actually done many years ago in this course. Okay, and in fact it went on to be a startup by the 2 students who were doing it. Didn't go anywhere, but okay. But yeah, I mean I'm talking about like 2004-ish, 5-ish time frame. Yeah, but anyway, so yeah, I think certainly could. I think just generally context using these kind of physical context and this kind of thing have a lot of value. The other thing that people can do stress detection is with speech. Yeah, but that's much harder. I don't think I know of ready software to accomplish it. Whereas for the stress side, I think you can basically scavenge that.
How do they measure physical activity? 'Cause I'd assume they
Accelerometers.
Okay.
Accelerometers, gyros. Okay. And GPS.
Yes.
Because it does tell you about where you are firstly, if you're at a gym, stuff like that, right? I mean, and also how you're moving. So again, yeah, I can point to some work. In fact, that on that space, yeah, some of the early work was here, my group and some others here at UCLA. So yeah, there is. So yeah, I think reasonable stuff to do. Okay, so let's pick this thing up. So. So we looked at the model. So again, kind of idealized, but still complicated enough. And I mean, a lot of so the basic model behind this thing is the very first version happened in like late 70s, but then a lot of complications around it, which caused the failure of like that Mars rover and those kind of things. They were worked out in late 90s and early 2000s, and some of the more subtle cases like how do you combine timing constraints with power and all are like much more recent. Okay, so what we seek to do is now we want to have tasks, and we are going to schedule them on a processor. And so basically the question we are looking at is what does the OS do in this case, right? So some sort of things to be aware of. So firstly, we are going to focus on single processor. Multiple processors is far more complicated for a variety of reasons, but just to give you an example, so if you have multiple processors, then even certain questions that are easy to answer certain questions which are easy to answer with a single processor become intractable with multiprocessor. To give you an example, intuition would suggest if I make a processor faster, then I can only do better, in the sense that if I was meeting all my deadlines, then I will continue to meet all my deadlines if I made the processor faster. It's not true with multiprocessor. If I make one of the processor faster, then the interaction between them can result in situations where the deadlines start getting missed. So there are sort of complications which come up, or things like if I give you a particular solution and simply ask the question, will it miss deadlines? That question can be answered efficiently for certain kind of scheduling algorithms, can be answered efficiently on a single processor and is intractable on multiprocessor. So multiprocessor is a much harder case, so we are going to stay away from it. Stacks. So we saw that when we talked about functions, coroutines, and threads, but basically one of the ways these operating systems is, do they have coroutines or do they have real threads? That is, real threads as in with their own stacks and stuff like that, versus are they really fake threads and really essentially coroutines? Address spaces, do do these threads, do these different tasks, do they interfere with each other, or are they do they have an illusion of their own memory spaces, or can they trash each other? Protection, we talked about that how there is a supervisory mode versus application mode. So are there any sort of mechanisms provided by the hardware to accomplish these? And is the set of tasks dynamic, static, all those kind of things. Now, so that's a high level distinction, but the core which really matters is what the scheduling algorithm is. Okay, so all these other stuff, important as they are, the most important thing, that attribute of the OS, is what is the scheduling algorithm it is using. And by that, basically all I mean is, how does it decide what process, what thread to currently run on the CPU? Okay, just that simple question. And we saw some of the issues around that last time, that there may be multiple tasks in the runnable state. It may be that I may want to bump off the currently running task just out of fairness, all those kind of concerns. So there are many ways to structure or to have this question, right? I mean, one way could simply be, once I give the task the CPU, I'll let that task run until it willingly gives up the CPU. At that time, because it needs some resource, for example. At that time, I'm going to now look at what the other tasks are runnable, and then I'm going to pick one of them. Maybe I'll pick them based upon a first in, first out type of queue. Maybe I'll do a random coin toss, whatever. It could be any such policy. The particular one we are going to look at, though, is called preemptive and priority driven. So the idea behind the preemptive means that if a task is currently running, but if some event happens, like a timer event or an external event, or maybe the currently running task did an event, then the OS may decide to bump off the currently running task, even though it's willing to run more, and then bring in some other task. So it's preemptive. And priority driven means that we are going to say that every task has a priority, and we are going to see what that priority means. And what we'll make sure is that it's the highest priority task which gets the CPU. So my rule is very simple. If an event happens for whatever reason, I'm going to see which task has the highest priority, including the currently running one. And if the highest priority task is different than the currently running one, then I'm going to preempt the currently running one and give the control to the higher priority task. Within this, then you can say, where are these priorities coming from? Well, these priorities could be static or fixed, or they could be dynamic. So what I mean by that is that one approach could be that each one of those tasks or the functions associated with those tasks have fixed priority. We just say task 1 has priority 10 and task 2 has priority 5 and whatnot. Or the other alternative is that we can allow for some temporal, some evolution over time. So like, for example, right now I have 5 hours to the deadline, maybe my priority can be low. But as I come closer and closer to the deadline, maybe my priority should go up. Right? So urgency becomes the notion of priority. You could also have priority based upon importance. A task which is going to protect the car from crashing is perhaps more important than a task which is aiming for fuel efficiency, let's say. Okay, so variety of consideration can come into play. But the underlying thing is, at any instant, the highest priority task is run. And this is when we have preemptive. If we have non-preemptive, then at every time we are, a task is giving up the CPU willingly, then at that time, whatever is the highest priority task is the one we are going to do. So scheduling algorithm in this framework basically boils down to the following. How do I assign priorities? Right? Everything else is prescribed, right? That the highest priority task will run, and we just keep track of those priorities. So it's really method to assign the priorities. That's really sort of at the heart of these things. And so what would your intuition suggest? What do you think would be a good way to assign priorities? What considerations do you think are more important?
Just based on like the real-time nature of the task, whether it's hard for.
Okay. So do you think that would be fine if, and the nature of task doesn't matter, whether it is protecting a crash versus fuel efficiency?
I don't know.
Okay.
Or maybe just like more fundamental, like just like how long the task is gonna run, I guess, or.
Okay, so you're saying the load it induces on the task, on the processor. That if it is more resource hungry, then it's higher priority.
Yeah, or like, I guess, to like maximize the amount of tasks that are running, and like reduce like the amount of idle time.
Okay. What other considerations do you think? No, all good points. And again, I mean, we'll see what at least this framework. Other things could simply be amount of money being paid, right? I mean, a user who's giving more money is more important than the user who's not, right? I mean, so financial considerations can come into play. So there are bunch of things there. Now, just wanted to mention that the Mbed OS, which we saw the diagram about, it is built on top of an underlying real-time operating system, so it does have the notion of priorities. Okay, so again, so what usually what the operating systems do is they provide you some either preemptive or non-preemptive priority-based scheduler, but they don't tell you what the priority is. Your goal is to provide the priorities. It's your job to provide the priorities for a particular thread. There are some systems which instead ask you to give them the timing constraints, like what the period is and what the deadlines are, and then they figure out the priority. Okay, so there are both type of thing. The latter is rarer than the former, but they both exist. So now let's talk about this priority notion a little bit. So just to motivate why priorities matter, so let's take a very simple example. I have a task with some period 50 milliseconds, a worst case execution time of 25 milliseconds. I have a second task period of 100 milliseconds and worst case execution time of 40 milliseconds. So if you think about it, what is the percentage of the CPU needed by the first task? So every 50 milliseconds it needs 25 milliseconds of CPU time. So therefore its load is 50%, and the second task needs 40 milliseconds every 100 milliseconds. So its load is 40%. So collectively they need 90% of the CPU. If they needed more than 100% of the CPU, obviously I can't handle this load, but 90%. So is there enough CPU time? Now, if deadlines were not an issue, then this is enough CPU time, right? I mean, if I was allowed, if I didn't have to meet any deadline, then I can, so it could be that I may not be able to finish an instance of task 2, let's say, before the next copy arrives. Okay, if I'm willing to tolerate that, then the fact that my rate is less, the utilization of the CPU is less than 90% is sufficient. All I'm doing is I'm queuing things up, but on an average, I need only 90% of the CPU, and therefore I'm fine. In fact, I can even slow down the CPU by whatever, roughly 11% or so, and I will still be okay, right? Because I'm allowed to queue up things, which basically means I'm allowed to add delay. So the challenge comes if I also need to meet the deadlines. And remember, our deadline model was that the deadline, relative deadline, is the same as the period. So we are basically going to say, whenever I get a copy of task 1, I must finish it before in 50 milliseconds, and this one I have 100 milliseconds to finish. So once you place deadline, then you cannot anymore just rely on the percentage CPU. You have to now analyze what will happen to deadline. And since we have two tasks, so we just have two possibilities. Task 1 is higher priority or task 2 is higher priority. And so what you see in this diagram is top case is the one where it's perhaps a little harder to read, but top case is the one where priority of task 1 is higher, and bottom case is the priority of task 2 is higher. So what's happening is, I think from the far you can there's a yellow task and there's a bluish task, okay? And yellow one is the task 1, blue one is the task 2. and we are going to assume that they both came at t equal to 0. So what happens now is they both came at t equal to 0. The yellow one needed 25 milliseconds, so it went up to 25, and it had 50 milliseconds to finish, so it comfortably meets its deadline. And then the blue one comes in, blue one starts executing. At t equal to 50, another copy of task 1 arrived. But until then, the blue one is running, so it got to run for 25 milliseconds. But it needs 40 milliseconds, so I still have some of that task remaining. But at t equal to 50, a new copy of task 1 came, so the blue one will be stopped, and the yellow one will again start running, the new copy of yellow one, and it will use the CPU until 75. And at 75, the blue one again gets to run, and it will finish at t equal to 90. So both yellow and blue met their deadline, and now the CPU is idle until t equal to 100, at which time both a copy of yellow and blue will again arrive, and then the whole process goes through again. So in this case, it's reasonable to say that the system will always meet the deadline. Okay, if they arrived at t equal to 0, both of them. It turns out that with a little bit of logic, you can convince yourself that this is the worst case that can happen, that yellow, which was higher priority, came at the same time as blue, which was lower priority, because if the blue came a little bit later, that's actually going to be a better case for it, because it will have more room to play. So the worst case is that I am a low priority person and I reached a queue at the same time as a high priority person, then my queuing delay is going to be the highest. So with that intuition, you can say this is the worst case can happen, and I'm able to schedule within that, no problems. But if you revert blue and yellow, now blue has the higher priority, they both came at t equal to 0, well, blue will occupy the CPU until 40, and therefore yellow will miss its deadline, because when it starts running 40, it only has 10 milliseconds remaining to meet its deadline, and therefore it misses the thing. So priorities matter. Task 1 being higher priority worked, task 2 having the higher priority did not work. What do you see about task 1 and task 2? Well, we make two observations, right? One is task 1 has a lower period, and the other is, or in other words, task 1 is more frequent, and the other is task 1 has a lower computation time. There. It turns out, as we'll see shortly, that it's the frequency which matters more. Okay, so it's not the percentage CPU time and all. What matters is frequency. That is, if we make frequency of the more frequent task to be the higher priority task, then I can then if I cannot schedule it even with that, I cannot schedule it any other way. Okay, so with at least with static priority. Okay, so that's a but what this is showing is that priority assignment matters, right? I mean, which way you, it's not sufficient to look at the 90% number, because that would work only if delays, only if deadlines don't matter. But once we throw deadline into the mix, we can't simply look at how much of the CPU is needed by the task. I have to look at, as I kind of alluded to just now, we have to begin to look at how frequent the task is. So, okay, so so that leads to something which I already alluded to, which is if I'm analyzing, and let's say I have a proposed priority assignment for the tasks, then how can I say whether the deadline will be missed or not, or will be met or not? And the answer is that we look under the worst case situation. And then what is the worst case situation? So as I motivated just a short while ago, that intuitively for the lower priority task, the worst case situation is that it entered the system, that is the corresponding event happened just at the same time all the higher priority events came, right? Because then that is the maximum delay I'm going to see, because each one of those higher priority events have to be processed, and perhaps more, because they further copies of them may arrive. So the worst case situation for a low priority task is that a copy of each one of the higher priority tasks that exist arrived at the same time as this poor event did. So that's called the critical instant. And if I can show that the deadline for this lowest priority, this low priority task that I'm looking at is still met, then it will always be met. And so in effect, what I have to do is I have to see what is the response time, that is, how long would it take for this task to finish under this condition, under this critical instant, and then if it is less than the relative deadline, I'm good to go. And I have to check this thing for every task. And for the highest priority task, all that matters is that C should be less than T. Okay, so that leads to this theorem of sorts, which basically says a critical instant for a task occurs whenever the task is requested simultaneously with a request of each one of the higher priority tasks. And that's the worst case situation that one would face. So you could see that in the this another similar example as before. I have two tasks with periods 2 and 5 and computation time of 1 each. So processor utilization of first task is 50%, processor utilization of second task is 20%, 1 over 5 and 1 over 2. If I do higher priority, we give tau 1 the higher priority, then something like this happens where it comfortably finishes. And if I give higher priority to task 2, higher priority task 1, but instead of computation time being 1, I increase the computation time to 2, it still finishes, right? I mean, so again, task 1 is coming every 2 time units, so and whenever it comes, it gets the CPU, so it came at t equal to 0, t equal to 2, t equal to 4, and then task 2 is squeezing in between, so copy came at t2, it finished comfortably because it went all the way up to 5. So I can actually have C2 equal to 2 and I can still finish in time, okay? Not anymore. So this under this period, I can go all the way to C2 equal to 2, okay? And while maintaining the same C1. If I turn things around, if I do task 2 as higher priority, then I would see that task 2 runs first, and then task 1 which will now get to run only at equal to 1, finishes at 2 just in time. So now I can no longer increase task 2 anymore, because if I increase the task 2 computation even by a tiny epsilon, then task 1 will meet its deadline. So while in this case both priority assignments are possible, assigning task 2 the higher priority is more restrictive. I can make less use of the CPU, in fact, in this case. Whereas the other way around, I could make more use of the CPU. I could have 100% utilization of the CPU, but not this way around. So case 1, where I gave task 1 higher priority, and again you would see task 1 was more frequent, seems to be better. It lets me get more out of the system. So that intuition led to what is called as the rate monotonic theory of priority assignment, but it basically says that assign priorities according to the request rate, according to the frequency, independent of the run times. So we don't have to worry about the C's at all, okay? So if I have 2 tasks, then the more frequent task, that is the one with the smaller TI, should have the higher priority. And that leads to kind of this observation, which was proven by some researchers long ago, which is, it basically says the following, that assign the priorities according to rate monotonic, more frequent, higher priority, and attempt to schedule it. Or try to see whether that schedule works. If it works, great. If it doesn't, then no other priority assignment can do it. With the caveat that deadline equal to period. That's a very important one, okay? And the other caveat, that is static priority, because of the way we are defining it. So essentially this gives us, what it says is that do the rate monotonic assignment, draw those diagrams the way I showed before. If all the tasks meet their deadline, so essentially you're kind of doing a simulation of sorts for some cycle. If all of them meet their deadline, I'm good to go. If it fails, don't bother trying with any other assignment. So rate monotonic priority assignment is the only one that you need to apply, and don't bother with another. Another check you can do even before that is check the utilization. If my overall utilization is more than 100%, then of course nothing will ever work. So you can do a sigma C over T should be less than equal to 1, and that's the first check. But the next check is simply this: rate monotonic, apply it with the recognition that relative deadline is equal to period, and static priority assignment, and tasks are independent. All those assumptions that we kind of made early on. Now, this is great, but the question becomes that can I do better than this? So there are several aspects to it. One is that right now I have to do these kind of simulations of sorts, right, to verify that whether for a priority assignment the deadline is being missed or not. And that's kind of painful because it's it's kind of proportional to the least common multiple of all the periods. Okay, so that can be kind of a long simulation, particularly if I have large number of tasks. So one question which comes up is, can I do a quick assessment? Now, what are we given? We are given the C's and the T's, and we know D equal to T. So by just looking at the C's and T's, can I tell you whether the task set is schedulable or not, without having to go through this thing? But the concept being that this is something I may want to do at runtime. The operating system may want to do. The user makes a call saying, create a thread. This is a C, this is a T. The OS needs to get back immediately. Yep, go ahead. I'm happy with it, or no, we'll miss the deadline. Okay, and so this what is called a schedulability analysis. That is the set of threads that I have in the system, will it be able to meet the deadlines, or will I miss the deadline? That assessment has to happen pretty quickly, and therefore it would be good to have some way of identifying whether a set of tasks is schedulable or not without going through this simulation type stuff. Now the answer to that is unfortunately no, you can't do that, but there are certain set of filters that we can create to come closer to for some cases begin to answer that. So to understand that, first thing to kind of realize is that, and something I already discussed, that I can take sum the ratios of C over T. So C1 over T1 tells me what percentage of the CPU task 1 needs. C2 over T2 tells me what percentage of the CPU task 2 needs. I add them up, I get the total utilization of the processor. And of course, if that is more than 1, then I cannot do anything. But as we also saw, if it is less than 1, then in general, I cannot schedule it because there may be some combination of deadlines where it will fail. I can improve the process. I can increase the processor utilization by increasing C's, right? If I increase the computation time of a task, then the corresponding C over T will increase, and therefore U will increase. The way you increase the C is by slowing down the processor. So remember, we talked about previously changing voltage frequency and all. So if power management comes into play, then power management is basically affecting the C's. It's not affecting the T's. Why is it not affecting the T's?
Still having the same.
Right, it's decided by the external world, right? I mean, me changing the clock frequency of the processor is not going to change the rate at which the samples are coming in. So, okay, so processor speed affects C. You could even imagine things like I use different processor speeds for different tasks. I can change them independently. While I'm in task 1, I use one frequency. While I'm in task 2, I use a different frequency. So you can play all sort of games like that also. Okay, U equal to 1 means that the processor is fully occupied. I have no laxity left. U less than 1 means that processor has some spare capacity. But it could be, as we saw in an example earlier, I cannot increase the C anymore because I'm just schedulable. Any further slowdown of the processor or any more increase of C, like I add a additional piece of code, some operation in the function may cause problems. So one of the disadvantage of this fixed priority scheduling is something that we saw, again, I'm going to go back, this example, is that that I cannot keep the processor fully occupied under certain circumstances. So again, recall in this one, each task was arriving, had a computation time of 1, task 1, which is at the bottom, was arriving every 2 time units, and task 2 was arriving every 5 time units. And since I gave high priority to T2, which is not rate monotonic assignment, I end up in this situation that I cannot increase the CPU time anymore. What's the processor utilization? And to convince you we can't increase the CPU time anymore, the challenge out here is the following, that if I were to increase C2 even a tiny bit, then this task would miss its deadline. So I'm kind of stuck with a utilization of 1/2 plus 1/5, which is 70%, which is not that great. Whereas the other way of assigning the task had let me go all the way to 100% actually. So, so we saw, we see that fixed priority can lead to situations where I cannot slow the processor down anymore, and yet there is spare capacity in the processor. So, in a way, what it is saying is that I'm paying for the deadline by having a processor which is faster than what I need purely in an average sense. And this is kind of equivalent to saying that for those cases where because of some tight constraint, I need a faster car, like those few moments where I need to, go very rapidly, but on an average we drive very slowly, but I can't afford, I still need a faster car. So oftentimes we face this in system that something becomes a bottleneck, and that dictates the overall speed of the system, the overall speed of the processor that we are currently going into. So even though rate monotonic way of assigning the priorities is optimal in the sense that if it does not work, then we know nothing else will work. It, in the worst case, can have processor utilization which is pretty low. Okay, that is a lot of the processor is kept idle. And idle processors are wasted dollars, wasted watts, all sort of things. So could we avoid that? Okay, and so that's one question. One thing which does come out is the following: that if I have task sets, and this is kind of a theorem, that whose utilization, that is the U, is sufficiently low, then I can always schedule them. In particular, that number is around 69%. It's 1/log E or something like that. But the main thing is, if U is less than that, then rate monotonic will always work. The challenge comes sort of higher than that. So this utilization factor is kind of a good measure of how efficient the scheduling scheme is. Now, there are other scheduling strategies which require priorities to be dynamic, which can let you make full use of the processor. Or another way of saying is they can let you use a slower processor than otherwise that you might need. So, a theorem that sort of falls out from the underlying theory, and again I'm sort of not going to the proofs and all at all. It basically says that if I give you n tasks with fixed priority assignment, then the least upper bound processor utilization, I'm going to explain that shortly, is u equal to n times 2 to the power 1 over n minus 1. So this is nth root of 2 minus 1 times n. What this is saying is least upper bound processor utilization factor. What this is saying is if I give you n tasks and their u is less than this, then I can always schedule them. And since we also told you that rate monotonic is optimum, that is, if it cannot schedule and nothing else, then it means that rate monotonic will work. Maybe some other priority assignment will also work, but rate monotonic will work. If u is greater than this, then it may be schedulable. And then your only resort is to take rate monotonic and do that simulation and check it out. Now, not the only resort, there's a better formula that I'm going to tell you later. More importantly, if you take the limit of this n equal to infinity, then it turns to be log 2, which is 69%. So which is saying for an arbitrarily large task set, if its u is less than ln2, then it is schedulable. If it is more than that, then it may be schedulable, but you have to check through the simulation. So this is a good threshold. So if I give you, let's say, 3 tasks, then for n equal to 3, I think this number is like 0.78 or something like that. Okay, so which basically means that if I give you 3 tasks and their utilization is 80%, then it may be schedulable. I have to check. If it is 75%, then I know it is schedulable because it's less than the threshold. Yeah.
This might be a dumb question, but how would you be able to determine like C1, C2, Cn if you just ran like a random function in code?
How do you know? So, I mean, that goes back to the original discussion. How do I know what the worst case computation time is, right? I mean, a couple of ways you do it. You do profiling. So you throw random data at your function, you plot, and usually you'll take like sufficient number of sigma over the mean. Okay, now that's not very gratifying. But there are tools which statically analyze the software and they find the worst case path and then they predict the delay. So such tools do exist, which are used in these kind of these are not your vanilla GCC or these compilers, but these are specialized compilers. But for most normal usage, you're probably going to do a profiling based. Good question though, because it's something that we ignore, but if you want to apply all of this, you need to know that, right? Okay, so yeah, so this basically is we can use this, but then if this test fails, that doesn't mean it's not schedulable. Now you have to go back to the critical instant analysis, effectively do that simulation of sorts to do it. And again, the critical instant analysis was the task schedulable when it arrived at its critical instant, okay? And I'll have to do that test. So in the closing seconds, I have 2 tasks. Is this task set schedulable? I compute u. U is equal to 0.41, which is comfortably less than this threshold. So yeah, it is schedulable. I can just not. I add a third task to it. Is this task set schedulable? Well, in this case, u is 0.86, which is greater than the formula threshold for n equal to 3. And so we can't say, we really have to apply the full-blown analysis, and in this case it turns out the task set is schedulable. You'll have to just sort of convince yourself. Now it turns out that there is a better formula which came much later, as in 2003, okay? And that formula is this, that if I take the utilization of individual tasks, so Ci over Ti, plus 1, take the product, and if that's less than equal to 2, then I can replace that original test by this test, okay? So instead of comparing u against that, I'm going to do this. The difference out here is, now I need to know C's and T's. It's not enough to know just u. Here I have to know the individual C's and T's. But if I do and check this, it turns out that this does much better. A lot of tasks for which the previous formula throws its hand, this will tell you whether it works or not. So it turns out that this is the best formula you can have if all you know are the CIs and TIs. That is, you have no other additional information, okay? Which is basically what our model started off with. So, so this is basically the best theory can do, and if this formula fails, you can you have to now do the full-blown analysis. So that full-blown analysis is called exact response time analysis, and I'm going to pick that up on the next lecture to show you how that is done. But it's essentially a stylized way of essentially an algorithm to implement that concept of simulation, basically. Okay. So we'll see you on Thursday. And again, if any of you wish to talk to me, I'm going to be in my office for a bit.